nicely also moves on to our next speaker, who is again going to span a different topic direction and a different.
You're muted,
Josie. I think you're muted.
I was muted. Sorry about that. So we'll start again. Thank you, Talina. We'll come back to you at the end of this session to join the panel. We're now going to move on to our next speaker, Sheila Macrine. So Sheila, thank you very much for joining us. It's great to have you here and have this additional perspective. So thank you very much for sharing the screen. We can see that nicely. So I'll hand over to you, and looking forward to hearing what you have to say.
I'm going to try and go back to the beginning. Thank you so much for this invitation. I'm a little bit a fish out of water in this conference, but our current research project is looking at a holistic view of embodied intelligence. I'm a cognitive psychologist. I trained in intelligence testing, alternative intelligence testing, moving beyond intelligence as an accumulation of knowledge towards a model of intelligence which shows the potential for learning. My research partner and I published a book with MIT Press last year on embodied learning for teachers and teaching and learning using embodied learning techniques, moving away from the dualistic model of brain-bound teaching and learning. And my area of expertise is in embodied learning. I was very enamored with Merleau-Ponty's phenomenology. As I read more and more about embodiment, I keep coming across embodied artificial intelligence, et cetera. And it really kind of triggered something with me. So my research partner, Jennifer, and I, along with Josie and Abdullah, are going to be publishing a book on an inclusive model of embodied intelligence to do some kind of crowdsourcing, sharing of labels and concepts across disciplines, transdisciplinary. So I'll get started here. So the relationship between human cognition and artificial intelligence goes way back. Certainly, if we look back at the conference at Dartmouth in the 1950s, where groups of scientists, mathematicians, cognitive psychologists got together to try to come up with some kind of mechanism to mimic human cognition, learning, memory, decision-making, to develop intelligent machines. Over the next few decades, the paths sort of diverged. Advancements led to distinct understandings of mind and intelligence within the fields of human cognition and artificial intelligence. So embodiment is sort of this kind of unifying, it provides a potential for collaboration. So despite the divergences in human cognition and artificial intelligence, they complement each other, especially when considering the role of embodiment intelligence across a diverse range of entities. And I'm going to talk about those diverse entities in a minute. But it is conferences like this that really will promote the sharing and collaboration across a wide range of transdisciplinary scholars, and I'm very delighted to be here. So embodied cognition, the scope of it is really widespread now across many disciplines. And there's one thing that when talking with the roboticists and cognitive psychologists, there's a lot of duplication of labels and concepts, but they're not necessarily really understood well among the different disciplines. So I'm hoping that this new project of ours is going to try and promote a real, transdisciplinary understanding of an inclusive model of embodied intelligence. So to begin, embodiment extends across a diverse life forms. And I'm very grateful to conversations with Josie, because I came from a very human-centric model of intelligence, and certainly in conversations that we've had over the past year and a half, I became more aware of how it's applied to animals and plants and even microorganisms, as our previous presenters talked about, and how they interact with the world through their bodies. Certainly animals have a remarkable sense of use of their senses, They utilize their bodies and senses in ways that showcase unique adaptations to their environment. The limitations of our human-centric notion of senses needs to be explored. These classifications are insufficient in understanding how many different biological agents, animals experience the world. The notion of perception without conventional organs. For instance, creatures sense their surroundings in ways that don't rely easily on defined organs, and further complicating our understanding of sensory experiences. And again, thinking is not exclusively human. We're going to look at that a little bit more. Non-human animals demonstrate intelligent actions, highlighting the intelligence manifest from across species. And challenging the anthropocentric view, these findings question the idea of sensory motor integration, linking sensing and acting, and is unique to humans, broadening our understanding of intelligence. Okay, sorry. Okay, so the philosophical foundations of this broad-based understanding of embodied intelligence comes out of the Merleau-Ponty's embodied subject, cognitive psychology, grounding cognition in sensory motor integration. Robotic pioneers, as you all probably know about Rodney Brooks's work with, he championed the idea of embodied intelligence with developing insect-like robotics, the Genghis robot, for instance, emphasizing the interaction in environment. The key scholars are Pfeiffer and Baumgart, who talked about how the body shapes the mind in terms of biological beings, and Pfeiffer and Idia pioneered the concept of morphological computation. Also, Clark and Chalmers proposed extended mind in terms of the tools and environment as part of cognition. More recently, Bongard and Levin, Josh Bongard and Michael Levin, advocated the integration of biological principles into artificial systems, where body shapes the mind again. And then Michael Levin's recent chain framework, which is a technological approach to mind everywhere, very interesting, a framework for understanding diverse intelligence. So the paradigm shift in traditional good old-fashioned AI to embodiment is really exciting. It shifts the focus from computation alone to include action, perception, prediction, environmental interaction. And it's really revolutionizing robotics, like the panel said. It aims to replicate the natural movement, learning, and problem-solving abilities found in biological organisms. So embodied intelligence arises from the dynamic interplay of the agent's form, environment, and cognitive processes, and operates on a spectrum of living, artificial, hybrid, and now living robots. We'll talk about that. And it emphasizes the adaptive, goal-oriented behavior, which Michael Levin calls the light cone, moving away from a centralized control. So bridging the biological and artificial intelligence, we look to the free energy principle as unifying framework for understanding how biological systems adapt and manage. It really helps to connect embodied and situated cognitive concepts. It emphasizes that intelligence as an emergent process in the interplay between the organism's form, environment, internal models. And the application to robotics leads to adaptive robotic systems of self-learning, self-predicting, and error minimizing. And this bridging of the gap really offers a way to understand intelligence across life forms and artificial intelligence, and helps shed light across diverse systems. So, sorry, I'm fighting a cold, I apologize. Mette Chiarelli at Columbia University stresses the importance that embodied agents need to, in designing embodied agents and building embodied agents, we need to break down the walls and shift away from siloed designs where mechanical engineers, software designers, and computational experts work independently and kind of put the agent together. He talks about this integrated approach to significantly improve the performance of embodied intelligent agents and considers all aspects of mechanisms, sensing, and computation as a unified whole to lead to a significant performance improvements. And this integrated approach is necessary because with embodied intelligent agents, all aspects of the system, physical, sensory, and computational, need to be built together because the components must fundamentally interact and interconnect to work in tandem. So what about embodied AI without bodies? So the group Gupta and team at Stanford came up with a deep evolutionary reinforced learning model called Unimals. It's very exciting. They're virtual robots with heads and limbs, and they're designed for evolution and learning experiments. They combine evolutionary changes with reinforced learning for adaptations. And so these Unimals learn to walk in different terrains and move objects. Quite frankly, they evolve and self-predict, self-learn, and then problem solve by mutating and adding limbs, removing limbs, changing limb properties. They also have offsprings that come that start to learn from scratch again, and they repeat the cycle and evolve and learn over hundreds of generations. So they speed up evolution that took millions of years for humans and living biological organisms in these virtual robots. So the implications are rethinking the requirements of embodiment. Can AI interact with the environment through simulations of robots? Can robots achieve embodied cognition without a conventional form? So bio-inspired robots would be a perfect example is our host, Josie Hughes's team, who created robots with remarkable dexterity of an elephant trunk and octopus tentacles. Rather than directly copying the form, innovations focused on spring-like spiral structure embedded in a soft robotic arm. And this design allows the arm to be both incredibly flexible and surprisingly strong. The result is a robot arm that can move, adapt, and manipulate objects with the level of control of adaptability inspired by natural counterparts. Bioengineering is another area that's really evolving. And this is where the tools can be used to create models that mimic or augment animal sensory systems, providing deeper insights into how animals perceive and interact with the world. And this aligns with embodied cognition principles. This also helps to enhance human cognition. Bioengineering holds promise for developing brain-computer interfaces, prosthetics, other technologies that can merge with and augment human cognitive abilities. It challenges the idea of intelligence, that intelligence is limited to human-like brains, opening up the possibility for diverse intelligences across organisms, cyborgs, robots, engineered life forms. Here's an example that Michael Levin's team at Tufts came up with, where they had a blind tadpole and they transplanted primitive eyes onto the tail, and the tadpole was able, the eye was not connected to the brain, but rather to the spinal cord, and the actual tadpole was able to react to light and learn through visual stimulation. Hold on, sorry. The next example is the Xenobots. This is by Baumgard, Levin, and Blackiston, and these are living robots. They're created from, they're AI designed with 100% biological, no engineered material. These Xenobots are really exciting because there's all kinds of implications about what they can do. They're microorganisms that can be used in medicine they self-replicate, they can work with people, hopefully the research will move to a point where they can help with disease control. So that's a really exciting area. So bioengineering continues to blur the lines between human and machine philosophical and psychological notions of embodied cognition. And we'll need to evolve in embodied cognition or embodiment to encompass new forms of intelligent life. This shifts and paves the way for future diverse intelligences encompassing organisms, cyborgs, robots, engineered beings with unique biological and technological compositions. Levin's work, for instance, posits that embodied intelligence needs to be seen on a continuum, suggesting that life forms continuously evolve greater cognitive complexity. And he talks about agents in terms of their cognitive light cone, which refers to the breadth of their goals that they can comprehend and achieve. Trying to get through this on time. So embodied cells and microorganisms is another big area. We talk about how cells and microorganisms have historically been seen as purely genetic, driven by purely genetic instruction, but now there's a new theory of sentient cell theory, which suggests that cells are more than biological machines, and it posits that cells possess a level of awareness, intelligence, and decision-making ability. It talks about intelligence, decision-making, and morphogenesis, which highlights how cells use bioelectrical signaling and interactions to guide body patterns and regeneration. And this demonstrates a form of goal-directed embodied problem solving that might be linked to rudimentary sentience. So some questions that are kind of really evident now from this work is that how does embodiment shape perception in living, non-living, hybrid, and living robots? And does the form or the nature of the body dictate how they experience the world? And what role might embodied cognition play in the further development of artificial intelligence and the understanding of the world, including form and environment? And are we stuck in a three-dimensional view of what the environment could be? Those are questions that really are interesting. And sort of coming off the last presenter, embodied emotion, how is embodied emotion differ across different types of entities? And does embodied emotion require a biological basis? And can it emerge from systems with alternative substrates? How about sense of self? How does a sense of self emerge from different forms of embodiment? What are the minimal requirements for a sense of self to exist? And does it apply to non-living and hybrid systems? What about cell sentience again? And then a phenomenological kind of embodiment. What does it feel like to be embodied in different ways? A human, a robot, a distributed computer system? And can we develop phenomenological methods to understand and compare experiences across diverse embodied entities? So this project is sort of looking at an inclusive embodied intelligence, a framework that focuses on goals, capabilities, environmental interactions across diverse systems, and moves from a rigid life versus machine classification. The emergence of an inclusive embodied intelligence is an ongoing interplay between the agent's form, physical and virtual, the environment, again, is it always going to be a 3D or virtual environment, the cognitive apparatus, the biological, artificial, or hybrid, and embodied intelligence emphasizes the adaptive behavior through environmental interaction, de-emphasizing centralized control. Broader implications are across disciplines, and it connects diverse researchers to promote interdisciplinary learning and a shared vocabulary. And finally, it has transformative potential, the ability to generate transformative change across fields and deepen our understanding of intelligent concepts. Is that good? Did I get in with 10 minutes?
Thank you very much, Sheila. Thank you. I think that opens up, I think what's going to be a really interesting discussion later with Matej and the others. As you said, there was a really nice overview from this other perspective. So thank you very much, Sheila, for putting that together.